Okay, so let's have a look at this given example over here. They've given us the derivative function, which is a parabola, and we have to now use this information to kind of determine what the cubic graph would look like, okay? So as part of my derivative function, I can see straight away I've got x-intercepts at -3 and 1, okay? And in fact, the turning point, which would be the halfway mark between the two x-intercepts, is going to land up being x equals -1 over there. That's your x-intercept. Okay, so -1. Right, what do we have to do with this? We've got to now just take notes of a couple of things to start off with. The parabola is a downward facing frowning parabola, okay, so that means it's a negative parabola, so the a value of your parabola or your quadratic equation is negative. That is going to follow through or carry through to the cubic, so therefore it is a negative parabola. Negative parabola. Therefore, the a value is negative. All right? And that means that the shape of your cubic graph is going to be negatively shaped, and that means it starts by decreasing, it increases, but it must finish off by decreasing. So we already know what kind of shape the cubic function is going to take, and we could establish that by looking at the shape of your cubic function. A frowning cubic function, negative cubic graph. Smiling cubic derivative function, positive cubic graph. Right, this is a really important part of the whole story here. All right, your derivative function, let's go back to the diagram quickly. Your derivative function has x-intercepts at the point of -3 and +1. X-intercepts is where y equals 0. All right, now if I take my y equals 0, that means these 2 points are where y, which is the same as f prime x, are equal to 0. Now let's think about what we know about that. When I let the derivative equal 0, what did we typically say that was? Derivative equals 0 is the turning points of your parabola. So the x-intercepts of your derivative function become the turning points of your cubic function. All right, so that's why I've drawn those little orange lines over there. And this is what I would typically say you need to do with this. If you've got a parabola, draw a straight line passing through each of the x-intercepts, okay? Because we should know that where we've got x-intercepts of a derivative function, that's where we're going to have the turning points of the cubic function. Learn that, okay? And then lastly, the turning point of your derivative function, so that's where the second derivative is equal to 0, okay, is at -1. Now, second derivative equals to 0 means we've got a point of inflection. That's where we're changing from being concave up to concave down or vice versa. So this middle line over here is where you've got your point of inflection, okay. Now, we don't have enough information to work out the exact coordinates of our turning points. We're going to have to estimate that, but what I do know is the shape. I know where it needs to turn, and I know where it needs to change from being concave up to concave down. Okay, so therefore my cubic function is going to take the shape of something like this. I know it's got to be decreasing. When it hits this orange line, it needs to turn because that's a turning point. This would be roughly your point of inflection, okay, more or less. And then it's going to carry on going, and when it hits this line over here, it's going to turn around and come back down again because we know that that's the shape of your graph. All right, and that's pretty much what you're going to have to know how to do, all right, is take it from a derivative function back to the cubic function. And in terms of a diagram, that's how we would do it. Okay, so learn those facts. X-intercept of derivative function is where you're going to have your turning points, and the x-intercept of your turning point of the derivative function is your point of inflection. As I say, if you've learned them, you know it, it's easy. All right, well done.